Part 3. Sorry for all the locomotion, commotion, that kind of a thing, but hope you guys are doing all right. Let's finish this, the kidneys off. We're just finishing off there on the DCT, the tubular secretion. And again, we've talked about it a number of different times there. This is kind of the fine tuning there in the DCT. Has the opportunity there to get rid of undesirable things, excess urea, uric acid, potassium. We've got the hydrogen there, controls the pH. There's your carbonate. So it's just a matter of fine tuning. This is a really good little recap. Sorry, it's kind of stretched. I try and stretch it, but you know, I mean, you guys can play with it a little bit here, print it off, do whatever you guys need to do, right? But this is a nice one. Thank you for... There we go, fine. Good enough. So, nice little recap of what's going on. Okay, in the glomerulus there, details. You've got your proximal convoluted tubule, your PCT, and it gives you details of everything there that I've said already. Okay, probably in more detail than needed, as a matter of fact. Okay, there's your descending and ascending loop of Henle. Descending, reabsorption of water there through osmosis. The ascending is water impervious, so these ions are going to be pumped out. There's your DCT, what's going on there. Mostly secretion, a little bit of reabsorption, okay? And your collecting ducts. So, that's a good little slide. Let's keep on moving, shall we? You remember there your NFT or your filtration rate there. Well, here we have the glomerular filtration rate. And if you actually calculate it, the kidneys are processing about 120 milliliters a minute. It's pretty crazy, eh? Can you believe 180 liters of filtrate is made every day? This is governed by a couple of things. The total surface area available for filtration. Why did it do that? The filtration membrane permeability. All right. And we've talked about the NFP there, your net filtration pressure. Okay. We are looking for at least 10 millimeters of mercury, okay, to get that stuff filtered off. The GFR is tightly controlled by two mechanisms. Okay. Your glomerular filtration rate there, you have intrinsic controls. This is renal kidney autoregulation. Okay, acts locally there within the kidney, but then there's also, it involves the outside the kidney. We've got nervous and endocrine function that also maintains blood pressure, and we call this there the extrinsic controls there. So GFR is controlled by intrinsic and extrinsic controls. Good. I have a... Yes. There we go. I'm losing my mind. Good. The intrinsic controls here maintains a nearly constant GFR, okay, in the range of about 80 to 180 millimeters. Okay, two types of renal autoregulation there. Like, again, this stuff here, I'm not really interested in. You guys can have a read it in the book, but I'm not going to go into MAP, okay? The only thing I'm going to go into is the NFP there, 10 millimeters of mercury. Okay, it's got to fight through the resistance there in the glomerulus. As well, what is your GFR stand for? I'm not going to go into anything too crazy. Tubulo-glomerular feedback mechanism. Forget about it. I'm not testing you on it. So let's move on, shall we? But... intrinsic controls, we've got something there called the myogenic mechanism. We're an increase in BP, okay? Constriction of the afferent arteriole. Increased BP, constriction of the afferent arterioles. That should make sense. Helps maintain normal filtration rate, okay? Protects glomerular from damaging high blood pressure. Okay, lowering the BP, dilation of the afferent arteriole, helps maintain. So there is movement on this. We don't want too high a BP because then you'll blow the glomerulus right out of the water, right? Okay, but you do need enough BP in there to maintain a good GFR. Okay, we want to maintain a good glomerular filtration rate. We don't want the BP too high. We do not want it too low. Okay, and with the help there of the juxtaglomerular cells and the macula densa cells, we're in good shape. Okay, now that was this one right here. We're getting to where I want to be right in here. When we get into the renin-angiotensin mechanism. This one here is a big banana. So this one, there's some interesting points in here which I'll go through. Okay. What was it? The flow-dependent mechanism directed by the macula densa cells. Again, there's your macula densa cells. If the GFR increases, filtrate flow rate increases. Kind of makes sense. If the filtration rate increases, the flow rate will increase as well. The filtrate of the salt concentration will be high because of insufficient time for reabsorption. So this is an interesting point. If the GFR is too high, the glomerular filtration rate, if we're just if just filtering and filtering and filtering and filtering and filtering and filtering and filtering, well, the flow rate through the tubule system is going to be too fast. Like these things, they take time to reabsorb. That's slide 58. So let me go back to here. So it takes time for these things there to be reabsorbed by the capillaries. But if the GFR is too fast, this stuff is just moving, the salt's not gonna come out. Okay, there is a certain amount of time that must be allowed for this stuff to pass through the system so that things can be absorbed properly, things can be secreted, and then in the DCT with the macula densa, they're watching. Okay, they're putting the icing on the cake here, secreting what needs to be secreting. Maybe there's maybe there's some sodium that needs to be reabsorbed, and wherever the sodium goes, what follows? What two things follow? Most importantly, water, and then also chlorine as well. Let's get moving. Where are we here? So the flow-dependent mechanism directed by the macula densa cells. If the GFR rate increases, the filter rate will increase as well, and creating issues. Okay, because there needs to be enough time for reabsorption to occur. The macula densa cells, okay, they respond to an increase in sodium chloride by releasing a vasoconstricting chemical that acts on the afferent arteriole. We're going to get into all this kind of stuff here. I'm not too interested in this slide, but we're going to get into, wait until we get into aldosterone. The nervous system under normal conditions at rest, the renal blood vessels are dilated. Okay, renal autoregulation mechanisms there prevail. Under extreme stress, norepinephrine, just another word there for adrenaline, is released by the sympathetic nervous system. Okay, epinephrine is released by the adrenal medulla. The adrenal medulla is on those two adrenal glands sitting on top of the kidneys. Both cause constriction of the afferent arterioles, okay, inhibiting filtration and triggering the release of renin. And this is where we're getting into renin right now. Renin increases BP. We're going to show you this right now. This video is awesome. Okay, pause the video, watch the video before you go into this, okay? The juxtaglomerular cells there, they release the renin, okay? There is normally angiotensinogen. It's just a plasma protein. It's present in your blood, okay, all the time. But when renin is released, renin and angiotensinogen, okay, they produce what's called angiotensin 1. Watch the video. It's good. Better than me. And with the help of angiotensin 1, with the help of the what we call ACE, it's angiotensin converting enzyme, and this is found in the blood there, especially there in the lungs. Okay, this forms a complex there with angiotensin 1. So again, ACE plus angiotensin 1 produces angiotensin 2. And you're probably thinking this is very odd. Here, the kidneys are, one of the kidneys just go from A to B. Why do they have to go from A to here to there to this, then to eventually get to B? Doesn't really make any sense, right? But this is how the endocrine system works. A hormone will be sent out, it'll form a complex with another, which will then trigger another hormone, which will then trigger another hormone, which will then travel to its end destination and do its job. That's how the hormones work. And I apologize, it's hormones come at the end. That's where they are, or just the whole mechanism there of endocrine system. So again, angiotensin, when renin is released there by the kidneys, it forms a complex there with the angiotensinogen, a plasma globulin there found in the blood, to form angiotensin 1, which then gets converted using ACE to form angiotensin 2. Now, angiotensin 2, what is all this? Angiotensin 2, and you may want to write this down here, but there's more of it. There's lots of slides with this, but the angiotensin 2, vasoconstriction. Boom. Vasoconstriction, tightening of those. That's my son. Sorry about that. Tightening, vasoconstriction, tightening of the arteries there increases BP. It also releases aldosterone from the adrenal glands on top of the kidneys there. Okay. They allow for what's called ADH, antidiuretic hormone, also called vasopressin. Okay. And antidiuretic hormone, antidiuretic. Think about it. Diarrhea, we know what that does. Water in the wrong direction. Antidiuretic keeps that water in the body. So what happens is antidiuretic vasopressin, it retains sodium. So it tells the DCT to absorb sodium. This is at the end of the game, right? DCT, your distal convoluted tubule, just before we're going down into the collecting tubes. Okay, the DCT is ordered. Look, retain more sodium. And what follows the sodium? Water. Okay, and that's what we're looking for. ADH also increases your thirst. If you're thirsty, sure, you're going to drink more water. What's more water going to do in your closed system? You remember your cardiovascular system is a 5-liter jar. It's closed. Okay? And if I dump more water into that, what am I going to do? I'm increasing the blood pressure. So you're by creating thirst, you're increasing the blood pressure, and by vasoconstricting the arteries, you are doubly, okay, increasing the BP. Okay? Good. And this is just another snapshot here. There's your angiotensinogen, okay, plus renin produces angiotensin 1 with the use there of the angiotensin converting enzyme, or ACE, which is generally found in the lungs. We make angiotensin 2, and vasoconstriction, increased aldosterone secretion there by the adrenal glands, increased ADH secretion, antidiuretic hormone, keep those sodium, keep the water, increase thirst. So it's all right here. Nice little slide. Like it. The effects of angiotensin 2, we've talked about them here. And anything there, this is what I'm looking for right here. I'm not looking for anything more than that. Okay? You know, in the book there, we're talking about MAP and all these. I'm not interested. Okay? If you can tell me that angiotensin 2 does all this and why, like there's 10 PhD papers in these 4 bullet points right there. So there's a lot of information there, and that's what I'm looking for So when the kidneys release renin, what's the end product? What do the kidneys want to do? Increase BP. They want vasoconstriction. They're going to make you thirsty. You're going to drink 5 liters of water, and you're going to increase your BP two different ways, okay? Yeah, it's all going over the same thing in just more detail than I care to go over. Okay, effects of angiotensin 2. Watch the videos. Don't worry about these ones here. There's this one here. Okay. Now, sorry. The systemic blood pressure. You guys can have a look at this. This was an interesting little diagram there. You guys can follow it all along and see where it takes you. I'll ask you guys about this there next week when we do the kidney, because I'm gonna put this slide up onto the main viewer there when we're doing the kidney lab. Okay, see if you guys can follow it. We'll come back to that one. Don't lose it. Differences there between urea and uric acid. Urea there is a byproduct of amino acid catabolism. Okay, breaking down. Plasma concentration reflects the amount of protein in diet. Urea enters the renal tubules through the glomerular filtration and contributes there to the reabsorption of water from the collecting ducts. Uric acid, though, a little different. It's urea is a byproduct of amino acid, where uric acid is a byproduct of nucleic acid metabolism. It also it enters the renal tubules there through glomerular filtration. Most reabsorption occurs there by active transport. About 10% can be secreted or excreted either way. So just little differences there. Urea comes from amino acid. Uric acid comes from nucleic acid. And urea, funny enough, was the first human-made organic molecule. And the university over in Prague, Czech Republic, the University, Charles University, they were the first anywhere to actually produce and create an organic molecule, which led to the amazing science of organic chemistry. So the birthplace of organic chemistry started with urea. All right, urine composition, about 95% water, usually contains urea, uric acid, creatinine, may contain trace amounts of amino acids, electrolytes, but no glucose. Volumes vary with fluid, okay. We are on the way out here. I'm just closing the door because the family's getting a little boisterous. But you'll see here the process of elimination as far as urine goes. We started off in the nephron, and then we move on to the collecting ducts. And then we're down into the renal papillae, major and minor calyces, the renal pelvis, okay? And this is what we've talked about so far. The end of the PowerPoint here, we're going to move from the ureter on out. Okay, ureter, bladder, urethra, and then to the outside. So you'll see here, there's your ureter, and your ureter, as you remember, that's slide 71. A lot of slides, eh? Too many slides, Ian. Where are my ureters? Right there. So these are your ureters right here, okay? And they connect the kidneys there to the bladder itself. About 25 centimeters long, extends downward, okay, parallel to the vertebral column, okay. Wall of the ureter. Here we've got a mucus coat, muscular coat, and a fibrous coat, okay. And there's your lumen, okay. The bladder itself, okay, the cells that I want you to know for the bladder, I will test you on this. Transitional, have a look at it, okay. You should have covered those there last semester in Bio 1031. If you haven't, let me know. Transitional epithelial cells, these are stretchy cells found there in the bladder. So as the bladder distends because of the urine volume, it's actually called the micturition reflex. The scientific word for going pee is micturation. And when these transitional epithelial cells stretch so much, it sends a message there to the brain, find a bathroom. So the bladder, hollow distensible muscle organ there located in the pelvic cavity. Okay, posterior to the symphysis pubis and inferior to the parietal peritoneum. The internal floor of the bladder includes a triangle area called the trigone, which has an opening, okay, at each of the three angles there. And basically, I'm looking for transitional epithelial cells that will stretch, okay. The urethra, you'll see there that the urethra of the male is longer than that of the female, and medically speaking, this tends to cause some issues there with female patients because the urethra is a lot shorter, okay, and therefore there the bladder is much closer to the outside external world, so the ability there to get an infection, a urinary tract infection, is more so, okay, than in the males. Okay. There's your micturition. Okay, you guys can have a read of that. Urinary bladder distends that fills with urine. Stretch receptors in the bladder are stimulated. The parasympathetic nerve impulse. Parasympathetic, this is rest and digest. You cannot go to the bathroom if a dinosaur is going to attack you. All right? Parasympathetic, rest and digest. Okay, when everything is safe, then I can go to the bathroom. Okay, and yeah, you guys can have a read of that. This is called the micturition reflex. Regulation of the urinary system, diuretics. Okay, they are out there that promote the loss of water. Okay, diuretic medication are very powerful. Okay, they slow the formation of the medullary gradient, which leads to much less water reabsorption in the loop of Henle and more excretion. Let's go that again because we've just covered that. These diuretics, okay, they slow the uptake of water reabsorption in the loop of Henle. Is that the ascending loop or the descending loop? Because there's only one of them. The descending loop is the only part of the loop of Henle that is able to absorb water. So what these diuretics do is they attack, so to speak, they don't attack, but they go after and they slow down water reabsorption in the descending loop of Henle. Okay? Angiotensin II receptors, blockers. Okay? They stop aldosterone production. Okay? Lowering BP and more water is excreted. Antidiuretic hormone. This is what we were talking about there before. ADH, or also called vasopressin. Okay, it's made by the hypothalamus in the brain, stored in the pituitary gland, and tells the kidneys how much water to conserve. Alcohol and caffeine slow the release of ADH. They actually cause dehydration. Okay, and are diuretics themselves. Okay, diabetes insipidus, inability of posterior pituitary gland to release ADH. Okay, or the inability of the kidney cells to respond to ADH leads to excessive loss of water, which can be very dangerous. Okay, regulation of the urinary system. Okay, you guys can have a look at this. ADH causes the kidneys to reabsorb water. We've talked about these right there. You guys can have a look at those. Okay, and the last slide there. Second last slide. Kidney diseases. Chronic kidney disease is the most common kidney disease and leads to kidney failure. Causes hypertension, diabetes. Okay, and it's a slow process. The kidney function can be determined by the GFR, and that's why I've introduced that there, the GFR. That will determine if your kidneys are working well or if they need an upgrade. As the kidney disease progresses, the GFR decreases. So as the disease progresses, the ability there for the kidneys to filtrate, goes down substantially. If urine contains protein or glucose, kidney damage is present. Once kidney failure occurs, the only treatment options are dialysis or a kidney transplant. Okay. I haven't been familiar with anybody who has labored through a kidney dialysis, but it's a lot of time spent sitting in a hospital room. Kidney stones. Kidney stones, they're about, I guess, 10% of the population. I've never had one. Knock on, knock on wood. Most common cause is excess uric acid or calcium oxalate. Okay, uric acid is a waste product there of the DNA, nucleotides. Uric acid builds up in the kidneys, causing stones. And that is the end of our urinary PowerPoint there for week 10. Please stop and start. Please watch all the videos. The videos are really, really great. And so just to recap, your assignment is due tomorrow, Wednesday, week 10, July 20th by midnight. Okay, there is no class tomorrow. All right, there's no class at all there week 10, or no class in-house. We have the 3 or 4 videos that I'm going to post right now to YouTube. And next Tuesday, there is no class at all. There's nothing scheduled because Wednesday we have the kidney lab. The kidney lab is posted to Blackboard. Have a look at it. Have a read through of it. It's not too bad. It's kind of the same thing as we're going to replicate the heart lab, but just with the kidney, and we're going to make it a lot easier on you. So I hope you guys are doing well. Please take care. Please drink lots of water. The heat is unbearable. If you have a little Mr. Turtle pool, go and get into it, because that's where I'm going right now. Thanks, guys. I appreciate your time. Sorry for the internet disruptions there. Those kids downstairs soaking up all the bandwidth, But take care. Email me if you have any questions. I'm always available. Take care, guys. Bye-bye.